All right, hi everybody. So today we're going to talk about forces on an incline. Now, an incline it refers to basically any surface that isn't completely flat. I think at the school we have the ramps. A ramp's an incline. A hill is an incline. Stairs are technically inclines. So anytime you are moving up a hill, like up a slope or down a slope, you are considered on an incline. So we're going to take a look at forces acting on an object, okay, while in an incline setup. So we have this, it's not a very practical situation, but let's say this. We have some incline, it's raised at 30 degrees. We have some box that's connected to the wall. So this vertical is the wall, okay? And we want to figure out what is the tension acting on this box, okay? So we want to figure out the tension acting on this box. Box has a mass of 7 kilograms, and it's a frictionless surface. So frictionless surface basically saying, okay, there's no friction whatsoever acting against it. It's just kind of hanging out there. So first step, okay, should always be to draw that free body diagram, okay? We should just follow our steps that we did before, okay? Now, here's where it gets tricky. So our box isn't on a flat surface like it was in the first example. Now we're kind of on this inclining situation. So when drawing my free body diagram, I am going to continue to draw it like it's on the incline. So I have my little incline and I have my little box. Now, due to the fact that our surface is now at this slant, okay, that can cause a lot of issues when using our X and Y axis because technically speaking, this slant is at an angle. It's at our 20 degrees. Well, that makes life difficult. So what we're going to do is because we've rotated our surface, we're also going to rotate our X and Y coordinate system. Okay, so the X-axis now follows the slope of our incline, and our Y-axis kind of goes off. So let's go in the free body diagram. So first and foremost, we have weight. Weight points vertically down. Okay. Weight points vertically down. There's going to be a lot of you who want to draw weight along like it's the y-axis here. That's wrong. It must be going vertically downward. Okay? Then, our normal force is perpendicular to our surface, which our surface is slanted, so my normal force should actually be a little bit different. And then last, we have tension. Okay, tension just follows the way we wrote. So there are my forces. Okay. Now looking at this, some of you might be thinking, okay, that looks fine, whatever. But actually we have a bit of an issue. So we've rotated our X and our Y axes to follow the slope. So we look at our free body diagram, tension falls on the X-axis. Force normal follows along the y-axis. But our weight right here is a little different. Our weight doesn't follow along the x or doesn't follow along the y. So because of that, whenever you have an inclined plane, okay, let me write that out. Whenever you have an inclined plane, you must include the following. So our weight right here is off. Okay? So what we end up doing is we end up through some nice geometric functions, which Mr. Carey or you know, one of the other math teachers, I don't want to say Carey because I know he used to teach geometry still at the high school. They could teach you one of the geometric functions, and we get a new right triangle. Okay? So, how this right triangle works is we take from where the normal force is, and I just draw a dashed line continuing down past it. And then draw another line that goes along the slope, and we get this, which this is kind of hard to see, so I'll redraw this out. We get something looks like this. Now, the reason why I say from some geometric function is whatever angle the incline is, it now becomes this top angle here. Okay? So whatever angle the incline is, this one's 20 degrees, this now becomes my top angle here. There's my little 90 from my right triangle. So now I have these two new sides of this right triangle, okay, based off the one right here. This vertical right here, so this one right here, that kind of follows along the force normal is called the force perpendicular. So that little upside down T is perpendicular. And then this bottom one right here, if you kind of think about it, it runs along this. This is my force parallel. Okay? These two equations, force perpendicular equals weight cosine theta, and force parallel equals weight sine theta, these two equations are an always. I would definitely have these things written down. I'll even star it, so it's even really more important. Okay? These are an always situation. These ones always never change. These equations are always this. Okay? All right, so we've now officially taken care of our free body diagram, okay? Weight, because of how we reorient our XY axis on inclines, weight is not along the X or the Y axis. Because weight is not along the X or Y axis, we have to create these other two forces called my force parallel and my force perpendicular, okay? So, step one is now officially done. Step two, remember that's the summation forces one, okay? So I'm going to do my summation of forces X equals MA, and my summation of forces in the Y equals MA. And I put MAY right there just to make sure it's a little different. Okay? So, X-axis. All right, let's think about it. I have tension, so I have T. Now, this one's a little tricky to understand, but I do have another force along the X-axis, and that is actually my force parallel. Yes, it's not drawn directly on the x-axis, but the way that it's oriented is it goes along the x-axis, hence it's parallel to your surface. Now, the way we figure out the force parallel is look at the slant, the slope, slant of our incline. So our incline is slanted like this, okay, and my parallel force is going down and to the left. Okay, well, the part we care about is towards the left. So this is a negative force parallel equals MA. Wait a second. And then for the y-axis, I have force normal, because remember that's along the y. But then I also have this negative force perpendicular. Equals MA. Okay, now, part two is complete. Tensions along the axis, directly along the axis makes sense. Parallel, because it is parallel to the x-axis, it's still going along the x-axis. It's not directly on the object. It's still considered the x-axis. And then how it's oriented, look at it's going down the incline. We go down the incline in this situation, that is negative. Okay, based on this thing. It's going towards the left, so it's negative. For the y-axis, force normal is up, force perpendicular is down. Force perpendicular is like can always be considered that one always being negative. Equals MA. Now, how this picture is drawn, okay, one thing that's safe to assume is this, that the acceleration in the x is 0. Okay, this block is connected via a rope. It's not moving. So the acceleration in the x is 0. Also, the acceleration in the y is 0. Okay? So, to solve, we really just need to care about this x-axis. Okay? So if this whole right side 0, I have tension is equal to force parallel. Okay? We have a force parallel equation, so let's solve it out. So I'm going to say tension is equal to mg sine theta. So 7 times 9.8 times sine of 20. Let's make sure we are in degree mode. So 7 times 9.8, sine of 20. And that gives me a tension force of 23.46 newtons. Okay? That's all I got. All right. Have a good one, kiddos. Talk to you later.